Reinforce algorithm. What is that? Reinforce is a type of policy gradient algorithm in reinforcement learning, and what that means is instead of trying to learn a value function like how good a state is or how good an action is, we go straight to learning a policy. And basically, a mapping from states to actions, or more accurately, to action probabilities. This particular method, reinforce, was introduced by Ronald Williams in the early 19th, and the idea behind it is pretty straightforward. We run full episodes, calculate how well the agent did, and then we adjust the policy parameters in a way that makes the good actions more likely in the future. So, if an action led to high rewards, the algorithm tweaks the policy to make that action more probable the next time. If an action led to low returns, we reduce its chance. And it does this using a method called gradient ascent, trying to claim the hill of expected return. And okay. Also, reinforce doesn't rely on any model of the environment, so no transition dynamics, no need to simulate outcomes. It just watches what happens during an episode and uses that to learn. That's why it's considered a Monte Carlo method. It depends on complete episodes before making updates. And alright, next part, actual workflow, the steps the algorithm follows. We start by initializing the policy. That just means picking some starting values for the parameters, maybe random, maybe from a pre-trained model, and these parameters are what we'll be updating throughout training. Then we sample a trajectory, we run an episode using our current policy. The agent moves through the environment, takes actions, receives rewards, and we record everything states, actions, rewards, all of it. And once the episode finishes, we compute returns. For each time step t, we calculate g sub t, which is just the total future reward from that point onward. You can think of it like a score for how good that particular decision turned out to be in hindsight. That's done. And next, we compute the gradients of the policies log likelihood. Okay, this tells us how the policy will change if we try to make that action more likely. We scale that by what was that uh, g sub t, so that better outcomes lead to stronger updates. Then we update the policy. We shift the parameters in the direction of the gradient. The step size is controlled by a learning rate alpha, and sometimes we subtract a baseline from g sub t. This helps reduce variance, and the baseline is usually an estimate of the value of the state. We are still pushing the policy in the right direction, but we are doing it with a cleaner, less noisy signal. And then we repeat over and over. We keep generating episodes, updating the policy, and slowly the policy improves, ideally until it converges to something useful. And okay, now we will go through the core steps of how the reinforced algorithm works. We start with a simple initialization step. We just set up our policy parameters, and you can think of this as the weights of a neural network that defines our policy. This policy tells us, given a state, how likely each action is. Once that's done, the learning happens in episodes. So for each episode, we let the agent interact with the environment. That gives us a sequence, states, actions, rewards from start to finish. We collect this episode by running the current policy. Okay, and that's done. Then inside that episode, for each time step, I mean from t equals 0 up to the last step, we do two things. And what are they? First, we compute the return from that time step. This is the sum of all future rewards possibly discounted by gamma if we are using it. And second, we use that return to update our policy. The update rule is take the gradient of the log probability of the action the agent took, multiply that by the return, and apply it to parameters using a learning rate. So idea is if a particular action at time t led to a high return, we want a policy to make that action more likely in that state. That's the core of the reinforced update. That's okay. And one problem with the standard reinforcement method is that it can be noisy. The variance in the updates can get pretty high. A common fix for that is to subtract a baseline from the return. So instead of just using g sub t directly, we use g sub t minus bst, where bst is the baseline and often a value function estimate. This doesn't change the direction of the update on average, but it reduces variance. And the gradient still points in the right direction, but with less noise. That helps the learning process stabilize a bit more. That is okay, and let me switch. So just to tie things together, let's look at a few key points about reinforced works under the hood. From a mathematical perspective, we are using something called the policy gradient theorem, you can see here. And what it says is that the gradient of the expected return with respect to the policy parameters equals to expected value of g sub t times the gradient of the log probability of the action given the state. So every update is really just pushing the policy to assign more probability to actions that resulted in higher returns. Now, how do we represent this policy? For discrete action spaces, we usually use a softmax over the outputs of a neural network. So for a given state, the network output logits and softmax turns them into probabilities over actions. For continuous actions, we typically use a Gaussian distribution. The policy network outputs the mean and standard deviation for that distribution, and actions are sampled from there. And here's the visualization part. Okay, what's happening here? The top graph shows expected return over episodes. So on the y-axis we have got return, that's the total reward the agent gets, and on the x-axis the number of episodes. What we usually see is that performance increases as training progresses, but there's some variance around that trend. You can see that clearly. Okay, and the solid line shows the average performance, and the dashed lines around it represent variability. That variance is why techniques like baselines matter. They help reduce this spread and make learning more stable. Now, in the second chart, we are visualizing policy updates in parameter space. You can think of the starting point is here, theta 0, as the initial weights of the policy, and as training goes on, each update moves the policy slightly, and ideally we get closer and closer to an optimal region, and here marked as theta final. Okay, and so that's what gradient ascent is doing, step by step nudging the policy in a better direction. And here advantages and limitations. So what are they? And let's start with the advantages. It is simple. The algorithm is easy to implement and doesn't require too many moving parts. It directly optimizes the policy, so you are not estimating a value function like in other methods. It also works well with continuous actions, and it naturally supports stochastic policies, meaning it can learn to randomize actions when that's helpful. And finally, it's model free. You don't need to know anything about the dynamics of the environment. The algorithm just learns from what it experiences. But there are trade-offs, of course, and the biggest one is variance. The gradient estimates can be noisy, which slows down learning. It's also not simple efficient. You need a lot of episodes for it to work well. And you only get updates after full episodes are complete, so there is no learning midway. It can struggle with long-term credit assignment to figuring out which actions were responsible for which rewards. And like many gradient-based methods, it can get stuck in local optima. And final part of this lesson here, our tips. So first, variance reduction. Subtracting a baseline is go-to method here. You can also normalize returns, reshape the reward signal, or use advantage functions that gets you into actor critic territory. And there is also something called natural gradients, which take the curvature of the parameter space into account for better updates. In terms of hyperparameters, the learning rate is critical. Start small, something like 0.01 or lower, and maybe decay it over time. And the policy network doesn't have to be huge. Simple architectures work just fine for many problems. For discount factor, 0.99 is common, but if you are working with shorter tasks, you might go lower. And you can also add entropy to the loss function to encourage exploration and click gradients to avoid large destabilizing updates. And finally, there are some useful variants of reinforce. What are they? The baseline version helps with variance, and GPO MDP uses per step returns instead of full episode returns. Actor critic methods blend policy gradients with value function estimation, and if you want to go deeper, PPO and TRPO are more advanced extensions built on these foundations. And there is also a deterministic version if you want to move away from stochastic policies entirely. And that's all for Reinforce. Thank you for listening.